Welcome to the 14th session on operating system and Linux. I'm Manibhushan D'Souza, and in today's class we are going to look at scheduling algorithm. Following algorithms will be discussed in this class. First come first serve, shortest job scheduling, priority scheduling and round robin scheduling. So let's begin with the first come first serve scheduling. In this particular scheduling, the process that makes the request first to the CPU will be the first one to be served. So this idea is simple. If you come first, you will be served first. In order to implement this particular algorithm, we maintain the first in, first you, first out queue. So this algorithm works in a very simple way. We have a queue here, and whenever a process enters into the system, the process control block of that particular process is added at the end. We usually use the linked list, but just assume that we are adding at the end. Whenever a CPU makes the request for a new process, the process that is there at the front of the queue will be given. So the newer process will be added at the end. The older process will be served first. So this is the idea that is used in the first come first serve algorithm. This particular algorithm is very simple to understand as well as to implement. However, because we are adding the process as they make the request, and we don't look at how much time a particular process takes to complete its task, the average waiting time in the first come first serve algorithm is in most of the cases is quite long. Let's take an example to understand how the first come first serve algorithm works. Now let's assume that we have three processes, namely P1, P2, P3, and let's assume that they require 24, 3 and 3 milliseconds to complete their task. So how do we use the first come first serve algorithm? If you draw a Gantt chart for this particular process, then we will notice that because the process 1 came first into the CPU, it will be served first. So it's going to take 24, let's say, milliseconds to complete its task. So from 0 to 24, the CPU will be occupied by the process 1. After process 1 completes, process 2 is allowed to do the task, and the process 2 will take 3 milliseconds to complete it. So from 24, that's the time that is taken by the process 1, we add 3 to get 27. After 27 second, that is millisecond, the process P3 is allowed to perform its task. So process P will take 3 milliseconds to complete. At the end of 30 milliseconds, all the process will be completed. Now let's look at the waiting time for every process. Now you know that process 1 enters immediately. So as soon as it comes, the process 1 enters into the CPU. So there is no waiting time for the process. So the waiting time for the process 1 is 0. However, process 2 is given a chance after process 1. We know that to complete the process 1, we require 24 milliseconds. So the process P2 has to wait for 24 long milliseconds to enter into CPU. So the waiting time for P2 is 24 milliseconds. After P2 completes, the process P is allowed to enter. That means to say that process P has to wait for the time of both process 1 and process 2. So the time that it spends in waiting is 27 milliseconds. So if you add all of them, you will notice that on an average, every process is waiting for 17 milliseconds. Now suppose if you change the order, and if you allow the process P2 and P3 to perform first and P1 to perform at the end, so what will happen? So first P2 will enter, and we know that P2 is taking 3 millisecond. So from 0 to 3 millisecond, P2 completes its work. After 3 millisecond, P3 is allowed to complete, and P3 also takes 3 millisecond. So after this much of time, that is after 6 millisecond, the P1 is allowed to perform its task. So what is the waiting? So waiting for P1 is 6, and waiting for P2 is 0 because it is the first one to enter. So it is 0 millisecond, and the process P3 will come after P2. So its waiting time is 3 millisecond. So if you take the average in this case, you will notice that there is a drastic change in the timing. So just by shifting the process, we notice that the average waiting time for a process drastically changes. Okay. One other thing that we must understand about the first come first serve algorithm is that it is non-preemptive. What is the meaning of saying non-preemptive is, if the process is allotted the CPU, then the operating system cannot take the process out of the CPU out of the process. That means the process has to voluntarily return the CPU back, either by making a input output request or by terminating its process. Okay. However, this kind of algorithms are not suited for time sharing machine, wherein the user wants to have an interactive session with the computer. So if the computer or if the processor is busy performing one task and it does not bother about the other tasks which are waiting on the queue, naturally this is not a suitable thing for an interactive session, because I type some command and I will have to wait for 1 hour for the CPU to just take my command and then start executing, which is not a great idea. We want the CPU to be shifted regularly across multiple users. So this is not suitable for that kind of situation. Now let's look at the other situation. In the other type of algorithm, that is the shortest job first scheduling, what we do is we associate with every process, we associate what is the time that it takes to complete its task. So whenever a process enters, we have to first figure out how much time it's going to take to complete its task. Okay. So if there are 10 processes are there on the ready queue, we just look at all the process and we pick up those processes which have the least time to complete its job. So in that's the word that is being written over here, the process that has the shortest time to complete its job will be the first one to be scheduled. So the shortest job will be the first one to be scheduled. So whenever a CPU becomes free, we look at the ready queue to find out which process has the smallest time. That one will be selected and then it is given to the CPU. Now the question usually comes, what if two processes have the same shortest time? That means let's say both the processes are taking 2 milliseconds to complete. Both are the shortest one. In that case, what to do? In that case, we go for the first in first out algorithm. So if there is a tie between two processors, the one that came first will be the one that will be served first. Okay. So the other idea that you can think of is the scheduling is done by examining the length of the process. Okay, so rather than what is the total length that is available. So but unlike your first come first serve, this is slightly better one. Let's look at this in a simplest example. So let's assume that we have 4 processes, P1, P2, P3, P4, and all of them have so much of time. Burst time is the time that it is required to complete its task. So that is the amount of time that is required by the CPU to complete its task. And you notice that P4 has the least amount of time, and P3 has the highest, P2 has the highest amount of time. So if all of them are there, if you start drawing a Gantt chart, how is it going to look like? So first we will take the process that has the shortest job to complete, and that is P4. So from 0 to 3, which is the time that is required by P4, we assign the process 4. After P4 is completed, we select the least among them, and that is the P1, and it takes 6 milliseconds to complete. So from 3 to 9, that is 6 milliseconds, we schedule P1. Once P1 is over, among them the shortest one is P3, which takes 7 milliseconds. So from 9 second onwards, P3 is started and it takes 7 milliseconds. So at the end of 16 millisecond, P3 will be completed. Finally, P2 is allowed to perform. So this is how the scheduling will work. Whichever is shortest is given the chance first. What is the waiting time, average waiting time? On an average, how much time does a process spends in waiting in the ready queue? So the P4 will not wait. So P4 will not wait. What about P1? P1 will wait for 3 milliseconds because it will be executed after P4. Then P3 will start after 9 milliseconds. Last one, that is the P2, will start after 16 milliseconds. So that means these are the waiting time for them. So if you divide by all of them, you will notice that average waiting time is 7 milliseconds. Okay, if you do a first come first serve algorithm, you will notice that it is a 10.25. So in any algorithm that you take, the shortest job first will be the one that will give you the optimal value. That is, it is going to give you the minimum average waiting time. That's why this particular algorithm is preferred. Okay. So what is the advantage? So if you are able to do the shortest job first, then keep the longest job later, you know very well the shortest job will complete very fast and they don't need to wait for a very long time. So the longest job anyhow, they are going to take longer time, so they can be put at the back, thereby reducing the average time that is required to do the work. Okay. There are two types of shortest job for scheduling. One is non-preemptive, the other one is preemptive. What is the meaning of saying preemptive and non-preemptive? So when the scheduler starts, if a new process arrives, in the non-preemptive, the new process will be completed only after the existing process completes it. So what do you mean by saying that is, suppose you have a ready queue with the number of process waiting and some process are waiting, and you have a CPU and the CPU is performing its work. So let's say CPU is doing its work. Suppose a new process arrives. So one of the processes is getting executed in the CPU. Let's assume that using the shortest job one of them was selected and then it is getting executed. But if a new job enters, in that case what happens? If it is a non-preemptive, this will be kept, no doubt it will be kept in the queue, but the existing process will not be halted. It will be allowed to continue even if it has less time. Suppose the existing process take 10 milliseconds to complete its work. A new process comes with the time of 2 milliseconds, so it's going to complete its task in 2 milliseconds. But one already, before it came, something else has already been scheduled and it requires 10 milliseconds to complete it. Now because it is already executing, it will not be preempted. So that's called as non-preemptive. In the preemptive, what is going to happen is, so a new process arises which requires 10 milliseconds. Existing process which is running on the CPU takes 10 milliseconds to complete. Now you notice that this 10 is higher than 2 milliseconds. So in that case, what is going to happen is, in the preemptive, so in case of preemptive, what will be done is, this existing process will be terminated and the newer one, whichever has come, will be allowed because it has less time to complete. So it just takes 2 milliseconds to complete rather than 10 milliseconds. So existing one itself is preempted and the new scheduling is being done. Okay. So the preemptive, wherein we empty the existing process, is called as shortest the remaining time first. That means we find out how much time it is remaining to complete the work and then we shift it. Let's look at a simplest example. We will first start with the non-preemptive. So here we have the processes, okay, as usual, but there is a arrival time. So you notice that at the time 00, P1 enters the system. Okay, so it has a burst of 7. Because it is non-preemptive, it is allowed. So at the 0 time, only P1 is there. If only one process is there, it will be definitely that itself will be scheduled. But after 2 milliseconds, so after somewhere at 2 milliseconds here, so 0 it is starting, P2 will come. Remember, look at the P2. This is 7 millisecond, okay, out of which it has used 2 milliseconds. So totally 7 was there, out of which it has consumed 2 milliseconds. So what is remaining? Remaining is 5 milliseconds. It requires 5 milliseconds to complete the task because it has already completed 2 milliseconds of its work. Now at 2 milliseconds, a new process will come, P2, with the remaining time as 4 millisecond, but because it's a non-preemptive, that will not be shifted. Look at what happens at 4 millisecond. So at 4 millisecond, what is the time it has consumed? So total it required was 7. Okay, so it has consumed 4 millisecond. So what is remaining at 4 millisecond? 3. Okay, so 3 units are still remaining, but what happened? P3 came at 4 millisecond, and what's the time it requires? It's just 1 millisecond, but still it will not be scheduled because it is non-preemptive. Okay, so after 5 milliseconds, you notice that one other process has come which has the 4, but after 5 millisecond, what is remaining with P2 is just 2 milliseconds remaining. So remember, total is 7. After 5 millisecond, 7 minus 5 is 2 milliseconds remaining. Okay, but whether it's remaining or not, it is immaterial. It only the one process will be scheduled. Now once this is complete, when it is going to complete after 7 millisecond, now remaining 3 will be checked. Now among them, which one is all of them have come here. Remember, after 5 seconds this has come, means all of them have arrived. So among them there is a tie. Which one has to be taken? So this will be taken first, that is P3 will be taken and then executed. So after that, now there is a tie because both of them are 4 milliseconds. Because P2 came first, it will be executed first, and then P4 will be executed. So this is how it goes. Now what if it was preemptive scheduling? In that case, what's going to happen? If it was preemptive scheduling, what will happen is, so at the 00, only one process was there. At the time 001 process was there, P1 is allotted. So at point at 2 seconds, what happened? P2 came. So at 2 seconds, what is the remaining time? So remaining time is not 5. So the remaining time of P1 is not 7. It's going to be 5 because it has already used 2 units of its work. It's already done 2 units of work. So now the situation here is there are 2 things are there. So which are the 2 things? One is 4, other one is 5. So which one is shortest? Shortest is P2. So P2 will be scheduled. So P2 is scheduled for how long? For next arrival. So what is the next arrival? At 4. At 4, how much has been done? P2 has used 2 units. So what is remaining with the P2 is remaining with the P2 is 2. But P3 is coming. What is the remaining with the P3? P3 has only 1 unit to complete. So immediately P3 will be scheduled. So at 5, P4 arrives. So at 5, P4 arrives. But what's the time with the P4? P4 requires 4 unit. Okay. So what happens? Among them, this is already over. So among them, now you have to decide which one is the shortest. P2 is the shortest, so it will be scheduled. After P2, which one? After P2, P4 is the shortest, so this will be scheduled. After that, finally, remaining P1 will be scheduled. So if you look at the average waiting time in the previous case, in the non-preempt, if you try to measure this 0, 7, 8 and 12, so okay, so where is the on an average? Okay, if you do that, what is this value? Okay, so you will notice that this is wrong. Okay, you will notice that this value will be higher as compared to the other one. Okay, so which is very less. The reason for it is you are scheduling, you are looking at it and scheduling, even though the scheduling is slightly complicated, but you can do it. The next one is the priority scheduling. Now we know very well in the multi-programming environment, multiple tasks will be executing. So we have to prioritize the process. So in the priority based scheduling is every process is associated with some priority, and whichever has the highest priority is given the CPU. Again, what if there are two process with the same priority, then we go for first in first out, that is FCFS queue. Who came first will be given the choice. So let's look at the priority based scheduling. Now if you look at this priority based scheduling, this is the special case of the previous one that we have seen, the shortest job scheduling. This is a special case of priority based scheduling. Okay, what is the priority in this case? In the shortest job first, what is the priority? You take the previous algorithm. In the previous algorithm, what we are doing, the process which has the highest weighting will be given the least priority. The process which has the least priority will be given the first choice. So what is the priority? Priority is 1 over, that is the inverse, 1 over 2, 1 over 7. Which one is having the higher priority? The one that has a small value, because we are taking it to the denominator, one has the smallest value will be having the higher priority. So it is using the inverse priority. Which one? Shortest job. The previous algorithm that we have just seen, that's actually a priority based algorithm, but it is based on the priority, and the priority is the job time. Whichever has the lower CPU burst, that will be predicted, that will be given the higher priority, and whichever requires more CPU time, that is a longer CPU burst, will be given a lower priority. Now let's look at the priority based scheduling. So we have 5 processes here, and there are some burst time that is required to complete them, but we have the priorities. So the one with the priority number 1 will be the first one, priority number 2 will be the next one, next is priority 3, priority 4 and priority 5. So this is how the process will go. So first one, if you notice here, the process P2 has the priority, so 1, so it will be scheduled. Then process 5 will have the priority 2, that will be scheduled. After that process 1 will be scheduled. After that process 3 will be scheduled. After that process 4 will be scheduled. So if you take the average, it's going to be 8.2, but you may say that that's too high or something, but we are prioritizing. Remember, priority is very important, because if the process is doing some operating system critical work, that has to be given the priority. It is like you are traveling, you are very busy, you want to reach to college, and you are traveling very fast in your bike. One ambulance comes. Now even though you want to reach to the college very quickly, you will have to give up to the ambulance, because you want to allow the ambulance to go front, because ambulance has the higher priority. So that's it, whether you are busy or not, it doesn't matter. Okay, so in the same way, there are some processes which have to be given the higher priority, and that has to be done whether we like it or not. Okay, now this priority can be given internally or externally. Now internally, the priority can be given based on the time, how much time it takes, how much memory it is required, how many files it is opening. Based on this criteria we can give it. The other external priority is outside the operating system, like the some processes which are generated by the users. They remember different types of users will be using the operating system. So in a multi-user operating system, many people are using the operating system simultaneously. So whoever has the higher priority will be given the chance. Like if somebody is paying higher, then they will be given the chance. Like you are working and I am working, so who will be given a chance? Definitely I am given the chance because I am your teacher. But if the principal comes, then who will be given the chance first? The principal will be given the chance first. So you know how the things are really working. So it is always the priority that matters. And in the priority scheduling, we don't say whether this is shorter or that is longer. Whichever has the priority, that will be taken first. Okay. One of the problem with the priority based scheduling is the indefinite blocking. So what's the meaning of that is the lower priority work will be indefinitely postponed. The reason, for example, you are working on a machine, so some teacher comes, some from other department, maybe English department or another. Then I will ask you, please get up. That teacher has come. You do your, you'll do later. Okay, let her do it. So after she completes it, somebody else will come from history department. So let's sir do some his work. You wait for some time. So you'll wait. Okay, sir, it's all right. After some time, the some office staff will come. I want to do something. So again, I will ask you. Okay, please wait. Let the office staff complete it. So you are waiting. After some time, principal will come. No, I want to do something. So principal will do it. So at that time, the entire day is over. So what you will do? You will go home. So that means you are waiting indefinitely, because why? Your priority is less. You are a student being a less prioritized person. You are starving. You are not given the resources. You are waiting for the resources. You are hungry. You want some resources. That resource is not given. Same problem will come with the processes also. The lower priority processes, when they enter, the system will say, see, there is a higher priority process, let me complete that and I will give you a chance later. So once that is over, next other higher priority will come. Then the system again says, please wait, there is one other higher priority, last one, I will, once it is completed, I will give you a chance. Once that is completed, somebody else will come. So this lower priority is waiting, and it is waiting indefinitely. So what is the solution for that? Solution for this is aging priority. So what happens is, as you are waiting, as you are waiting, you become furious. If you go to hospital or when you are waiting in queue and if the queue is not moving, you get agitated. So same way here, what we are doing is the process, when it enters, it is having a low priority, but after some time its priority is slowly increased because it is waiting. So it came first, even though you are, so if you are waiting from morning and some staff will come and say, sir, I will do it. So what I am going to say, see sir, this student is waiting from morning, sir, let him complete and I'll give you the chance later. So what I am doing is, even though you have, as a student, you have less priority because you are waiting, I am giving you a chance. So I'm saying, sir, from morning he is waiting, sir, let him or let her complete that work. So here, because you are waiting, your priority, even though you are a student, your priority is less. As you wait, as the time passes by, your priority slowly increases. This idea is called as aging priority. Okay. So by aging priority, we can get rid of that starvation problem. Let's look at the last thing, and that is the round robin scheduling. So this is designed for time sharing system. In what is the time sharing system, by the way? So in time sharing system, the CPU time is shared equally among all the users. So I am given some time, then somebody else will be given some time. So the existing CPU time is shared across multiple users. Okay, this idea is same as first come first serve, but with the preemption. So what is the meaning of saying preemption? In first come first serve, what will happen is, whoever comes first is given the choice first. Here also we do the same thing. Whoever comes first is given the chance first, but there is a limit. They can't go on and on. So the person who came first, we give them the system and we say that after 5 minutes you have to get up. Okay, after 5 minutes somebody else will sit. Whether you complete or not, I don't know. So you came first, use the machine for 5 minutes. After 5 minutes, somebody else will use it. So this is preempting. So whether they complete, if they complete it within 2 minutes, well and good. What, there is no need. If they say no, 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 I want 15 minutes time. Okay, 5 minutes you work, complete it, save it. I will call you again. Continue after this person completes it. So for every 5 minutes, one person is given a chance. So this is called as a round robin scheduling. So in this scheduling, what we have is a small unit of time. So that is called as a quantum. This quanta can be 10 millisecond or 100 millisecond, it depends. Okay, a small time is given, like I told you, 5 minutes for every person. 5 minutes is given, but 5 minutes is too much on a computer. So generally it is a 10 millisecond or 100 millisecond is given for every process. Within that 10 millisecond, or that is called as a quantum, within that quantum it is supposed to complete it. If it is not able to complete it, after some time again the next quanta is given. So you are given in small dosages. How you get the medicine, you don't get the entire, people, the doctor will not take, okay, take the one bottle full and drink the full tonic in one shot, then you will have other problem. So doctor will say, okay, morning one, afternoon one tablet, evening half a tablet, like that. In dosage, small dosage it is given. In the same way, in a small dosage, here the CPU is given for every process. So how does this particular process will work? We are using the circular queue, and what is this circular queue? So in circular, I hope you're familiar with that. Circular queue will start like this, and the last element will point to the first element. So you know that, I think. Hope you remember this circular queue. So you have one element pointing to the next element, pointing to the next element, pointing to the next element, and what will happen to the last one? Last one will point to the first one. That is called as a circular queue. This is the same idea that is being used. So what happens? For every quanta, one process is given. So this is one quantum. Quantum is 10 millisecond or 100 millisecond. So you just tell the process 1, I will give you 10 millisecond, complete it. If you can't complete it, after 10 minutes, vacate, that's it. So after 10 millisecond, what happened? Second one, process 2 is called. Okay, you continue. So I will give you one quanta of time. If you complete it, well and good. If you complete it before that, tell me, I will schedule the others. If you don't complete it, I will give you a chance when I come back. Okay, next, third. Okay, again we will give one quanta of time and ask, okay, you complete it. Whatever you can complete it within that quantum, you complete it. After one quantum, we shift to the fourth one and we'll say, okay, you complete it. After this, what happens again? First, we'll come back to first and said, you didn't completed your work last time. I'm giving you one more quanta, complete it. Again, we go to the second one. You say complete it. If somebody completes it, we continue with the queue. So you know very well how the queue really works. So this is the idea that we are using in the round robin scheduling. So in the round robin scheduling, we keep the ready queue as a first in first out queue. Okay, so every new process that comes in will be added at the end of the queue. This is a circular queue, remember. So we add it at the end of the queue. So CPU picks up one of the process, whichever that came first. It will schedule it for one quantum. After that, it is interrupted and it dispatches the next one. Okay. If suppose if a process completes before one quantum, then it's that process itself voluntarily it will come to the CPU and say, my work is over, I don't need one quantum of time, so give it. So during the examination you are given 3 hours. After that you are supposed to stop whether you like it or not. But some people half an hour they complete and go. Well and good. So if you are able to complete it within half an hour, it's a good thing. But maximum is 3 hours. Okay, so that's the same idea that is given over here. So maximum is one quantum. Before that, if you give voluntarily return the CPU so that others can be scheduled. Okay, but if you are waiting for longer than that, then you write a supplementary. So that's simple as that. Okay, so if you can't complete the subject within the 3 hours, then come to the supplementary and complete it. So that's the idea. Here it is not the case. It is what we are saying is, we give you one quanta, you try to complete it. If you can't complete it in one quanta, then come again for the next round. So you will be taken back after the next round and you can continue. Let's look at a simplest example with the three processes. So we have three processes here, P1, P2, P3. Let's look at how the things will go. So let's assume that the quanta is for 4 milliseconds. So that's the time that is being given here for demonstration purpose. So P1 came first, so you allot P1 for 4 seconds. So what is remaining after 4 seconds? It was 24. Now what is remaining with the P1 is 20 because 4 is already used. P2 is 3 milliseconds. So what happens, even though quanta is for 4 milliseconds, it completes it within 3 milliseconds and comes to the CPU and say, mine is over. So CPU say, okay, I will go and call the others. So it will call the P3 and it will call P3, okay, CPU is free, come. It will also say within the 3 seconds, that is say 3 seconds, it comes and says the CPU, my work is over. Okay, well and good, go. Now who is remaining is P1. So every quanta it is going to be given. Remember, it is given in quanta, it is not going to give it in full shot. The reason is after every quanta there will be interrupt, but because nobody is there, then you are the only one. No? If nobody is there, what to do? That will be itself will be scheduled next. So this is how it's going to complete it. And if you look at the average waiting time, it's going to come to 5.66 milliseconds. So the round robin scheduling is a preemptive scheduling. If there are n number of processes in the ready queue, suppose if you have n number of processes in the ready queue, okay, then each process will get a time of 1 over nth. So if you are equally dividing, so if the, you have played cricket match, how you will get 1 over for everybody. So everybody has to be given. So total is 3 hours. Everybody will be given 1 over. So total is 3, 1 over that. You are given a chance. So same thing, n process are waiting, 1 over that is given. But if the process requires a q amount of time, how much time it has to wait? It has to wait n minus 1. Remember, if there are 3 people, how long you have to wait? You have to wait for 3 minus 1. Why 3 minus 1? So this is the first one. 3 minus 1, what is 3 minus 1 is 2. This is the first one. Second one, next is your chance. If you miss it, again, first one, second one, next is your chance. So if you require a q amount of time to complete it, how long you will have to wait? N minus 1 into q time to complete that process. Okay. Now the performance of the round robin scheduling depends on the size of the quantum that we choose. If you choose a quantum very large quantum, it just becomes first come first serve process, because you know very well. Suppose if you give a quantum of 1 hour, what will happen? You start the one process, it completes in 5 minutes and say mine is over. So it is not interrupted because the quantum itself is 1 hour, very long time. Second one will come for 15 minutes to say mine is over. So there is no context switching from one process to the other. So if you give a longer time, the process itself will voluntarily say that I don't need, my time is over, I have completed my work. If you, that is a very long time. What if you give very short time, 1 second? In that case, the CPU is shared equally between them. This is called as process sharing, because every 1 second, 1 over n, the CPU starts switching. So it is a one way of doing it, but it depends on which one you'd like to use it. So that's all in today's class. If you are really interested in knowing more about it, please refer the Galvin's book on operating system. Thank you for your interest. We will meet again in the next class.